Hello, everyone.
Hi, Jamie. How are you?
Who's that?
That's Katerina.
No,
Hi, Katerina.
Jamie, don't you get it?
Hmm? What?
Just now you just asked me who was that.
Who was? Sorry, you lost me.
Never mind.
Sorry. This is on replays now, and it's totally got me being totally stumped by something I'm totally missing. Anyway, hi, Katerina. How's vacation?
Hi. Everything is good. Thank you. How are you? How's your summer?
Very warm over here. Very, very warm. Heat alerts over here.
Oh, yeah, same in Germany. Yeah, I heard. And in Portugal was the same. So, how is it? You don't have AC, I guess, so.
Sorry, I was just sharing the room. No, we don't really have AC. It's not really a thing here. Not really ever had to be one. We've got fans, obviously, and stuff like that, but we don't have AC. If that's what you asked, in case I misheard the question. Do you have anything on the agenda today, Katerina? You going to another beach today? What's your plan?
Oh, today?
Hmm.
I don't know. The weather's not too good today, so we were, um, I don't know, different things, but nothing special. Thank you.
I was reading up on the qubit teleportation, and it sounds really, really cool. I'm actually quite looking forward to um, the guest, the doctor's explanation on it. I want to understand it better. I don't understand qubits very well. This is why I love Science Society, though. I always come away a little bit smarter, or at least more comfortable with being confused. There's always something to way to grow here. I love that. Welcome, everybody. Thank you for coming.
We'll start in around 3 minutes. Thank you, everyone, for coming. Yep, we'll it will be an exciting room. I agree, it's really interesting, and yeah, let's see what we will learn today. No, it should be really interesting. I had the chance to look at the presentation, and you right now have a chance too. So I'll share actually the Nature paper in the chat really quick. Thank you.
Cool. Involving teleportation. I'm there. But it's not like Star Trek teleportation though. It's qubit teleportation, which is different.
I just watched the latest episode of Star Trek: Strange New Worlds, so this is fresh in my mind. I'm ready. I'm ready for this.
Did they actually cover qubit teleportation in Star Trek Strange New
No.
Worlds?
Hi, Hans. Oh, sorry. Hi, Hans. How
Hello.
are you?
Good.
Can you
Oh,
hear
Thank you.
us well?
hello,
Sorry?
Doctor.
Hi, Hans.
Hey.
Yeah, so I'm not sure if you met Cecilia, him, and Jamie yet. Welcome, and yeah, meet our co-moderators, Cecilia, him, and Jamie. And yeah, thank you for coming.
Yeah, no, we were in the
Yes.
onboarding room, remember?
Yep,
Exactly.
Yeah,
yep. We go back a long way.
very long way.
Nice.
How's your day today?
Yeah, great. It's really warm here in the Netherlands. But yeah, I think it's a common theme now.
Absolutely. Likewise over here as well. We've got like heat warnings and stuff like that over here
I
too.
see. Yeah. Yeah. Can you hear me
No,
well, or should I change
very
something?
well.
Okay. Nice.
Very, very well. Thank you.
Yeah, everyone is very excited about this discussion, so we really appreciate you coming. If you also look into the room chat, it's on the left hand, the little speech bubble. People share how excited they are. Thank
Ah,
you,
nice. Yeah.
everyone, for coming. Okay, we'll start in 1 minute. Let me just share on Twitter that we are starting. And I'll start with the introduction, and then we will go from there. Perfect. Okay, so welcome everyone to the Science Society here today, and a special warm welcome to Hans Beukers. Um, he is our guest speaker here today, and yeah, as I said, we are very excited to hear about your work. And before we do that, let me give the audience a little bit of background information so that they get to know you a little bit. Hans Beukers studied both physics and was also in medical school at the University of Groningen. And he did his master research projects for physics at the QTech lab of Ronald Hansen for medicine and cardiac electrophysiology at the Leiden University Medical Center. Then he decided to continue with his PhD in physics at the lab of Ronald Hansen. He is currently working on three-party remote entanglement and quantum network consisting of nitrogen vacancy centers in diamond. And he is also researching tin vacancies centers in diamond, and which is a new promising platform that might alleviate the main drawback of the nitrogen vacancy centers because it's low entanglement generation rate. And in his spare time, if you can believe, like studying medicine and physics, like he has some spare time, and he likes to play double bass and bass guitar, and he is the member of the QTech band, which had the honor to play during the QTech summer barbecue and the Christmas party. And during the summer, he likes to spend his time on the water on different type of sailing boats. Sounds like a very amazing, interesting life you're you're having. So congratulations on that too. And before we go into your presentation, Cecilia and Jamie would like to ask you like a couple of general questions, and then you're welcome to start with your presentation. Thank you, Hans.
Mm-hmm.
Yeah, thank you so much, Hans, for coming here to share your work with us. That bio that Karina just shared with us is very fascinating. So we just want to ask you a few questions about yourself just to get to know you a little bit better. So I will start off, and Jamie can continue. So yeah, I just want to know, how did you get interested in science? What was it that got you, into the idea of being a scientist and doing research? Was it a person? Was it a situation? Was it something you learned at some point? And also, how did you come to, study what you're doing right now?
Yeah, so thank you for the introduction. Yeah, I think it was quite a gradual process. So I started out studying medicine, and in the Netherlands, it's free to do other courses if you like. So after 2 years, I missed a bit physics and math. So I thought, let's follow a few courses, and this escalated to the whole study because I just thought it was really interesting. And then at some point, I did my master project in the group of Ronald Hansen. That's also my current supervisor, and there I was just really fascinated in the lab, being able to see all these really exotic effects like entanglement and superposition of quantum systems, all these things that only work out in math. You have the feeling, and that's really a different world. But if you're then able to see that in the lab, I thought that was really fascinating. And this kind of slowly lured me into doing more science. And at some point, I decided to do my PhD then.
That's absolutely fascinating. And
Yeah, maybe
also,
maybe I can add one thing that really I think was a a moment, right? You
Yeah,
asked for a
yeah,
moment.
no, go ahead.
I think what was really interesting to me was at some point we were trying to do a qubit rotation in the lab. So then you try to change the quantum state, and we were not succeeding. At some point, the postdoc said that it might be a leaking laser, and what turned out, we were measuring all the time our quantum system, and in that for that reason it was not able to evolve. So we were kind of, it's called the quantum Zeno effect, and I thought it was so fascinating that you could see this effect, that there was some leaking laser light, that there was a quantum system not able to evolve because it was being measured. And I thought that was kind of these moments that you think, oh, this is really cool, this is where I want to spend more time on.
that's really interesting. And also to back up Sister Raheem there, you make my life so boring, Hans. That's such an incredible bio that you've got. That's amazing. And is this what led you up to looking at qubit teleportation specifically? What is it that gave you that? Was this you trying to solve a problem, or was this you wondering could this be done?
No, so I think we're in a quite a specific part of science where it also sometimes the previous thing leads to the next thing. So the group was founded in 2008, and at that moment people were working on trying to measure these NV centers and experimenting whether you could measure a single one. And then slowly this built up to 2012, making entanglement, 2015 the loophole-free Bell test, where you can prove that quantum physics is like a real thing and that it is really a fundamental part of of physics. And so this was kind of the next thing. So we had previous PhD students in our group had made entanglement between two distant NV centers and had done some really cool experiments. And this was kind of the next kind of logical step. So it is, I think, sometimes science is really driven from kind of having an open question uh, and really striving to get there. And I think in our field, it also sometimes is that you try to push as as hard as you can and see what comes out. And I think this was kind of what happened here. That each time you think you kind of are at the limit what is possible, and then with some hard work you can get a step further. And this is, I think, also what happened here. So we had 2-node entanglement, and then we built a 3-node network, and then in the end we were able to teleport through this in this network.
That is definitely an incredible way to build us up to the talk. Thank you so much for answering our
Yeah.
questions. And unless Sister Raheem, you have anything else?
No, no, I'm good.
No?
Thank you so much.
Okay, awesome. And in that case, then, Doctor, the floor is yours. We are all ears. Thank you.
Great,
Oh, and
thank you.
one more thing, one more thing. Would you be happy to receive questions like during the presentation, or would you prefer we waited till the end? Because this is
No,
meant to be for your mind.
during the presentation is great. Yeah.
All right, thank you. Thank you very much then. Then the floor is yours. Thank you.
Thank you. So I try to make some presentation which is accessible for a broader audience. So hopefully in the questions we can fill up the gaps that I maybe left if I didn't start from the basics enough, or maybe go a bit more in depth if you have more in depth questions. But I would like to kind of give an outline of what we did. So okay, if we start from the first slide, you can see some artist impression of one of my fellow PhD students making how our 3-node network looks in the lab. So you can see we have 2 optical tables, and they host our 3 quantum nodes. So you have one in one separate room, and 2 are on the same table, and it is like really separated by meters. So such a table is a couple of meters long, and you can really see it is not on like some microscopic scale that we made this entanglement, but really on the meter scale. And so in the second slide, you see some artist impression of a quantum internet, and maybe this is a really important starting point to elaborate a bit on. So in quantum technology, I think there are 3 main routes. So the most known is, I think, quantum computing. So what all these 3 so the 3 ones are quantum computing, quantum internet, and quantum sensing. And what they all have in common is that we're slowly able to really manipulate the physics on the smallest scale that is possible. So really on single atom, single electron scale. And we're trying to build new technologies from this. And if you use this control over the smallest scales to build a computer, it is a quantum computer. If you try to build a network for communication out of it, it is a quantum internet. And if you use these smallest particles to measure and to get measurements, then it is quantum sensing. And I think quantum computing is the most known, maybe after this quantum networks, and lastly this quantum sensing. But I think maybe in maturity, maybe quantum sensing is the most mature one, right? Quantum sensing also, for example, the atomic clock is in principle a quantum sensor. It is some atom that spins around this axis, and we measure how fast it spins, and we base our time measures on this. So quantum internet fits into this field of quantum technology as one of these 3 pillars. And at our institute at QTech in Delft, we investigate the quantum internet and the quantum computing, and see how we can make this a reality, to push it also, to make it really sophisticated in the lab, but also try to make demonstrators to get it out of the lab. And the idea behind the quantum internet is to have some quantum nodes that can communicate with each other. So if you compare to the classical internet consists of different computers, but what makes the internet an internet is that it is a network, right? So if you want to connect or send an email, for example, to me, we don't need to share a direct connection, but there is a network that takes care of routing your message to me. And the same idea holds for the quantum internet. So we envision these multiple nodes that are all linked together and that can route this sending of information. And the difference then between a quantum internet and the classical or the normal internet then is that it can't just send like normal information, bits, as the classical internet would do, but it can send these quantum bits, these qubits. And the difference between those is that the classical bits can be a 0 or a 1, but in quantum bits we use these states, the state 0 and the state 1, and so it can also be in a superposition, so being a combination of these two, or be entangled with each other. So kind of we can use this full potential of having this qubit as a building block of information. And a logical new question would be, okay, if you have such a quantum internet, what could you do with it? And also there, I think, are three options. First one is privacy. This is, I think, also the most mature idea, where you can use a quantum internet to have unbreakable communication. So we currently use like hard math puzzles to encrypt our data, but using a quantum internet or a quantum link to send our data can do this inherently in a secret way. You can also think of blind quantum computation, where you do computations on a server where the server doesn't know what it is calculating. So this is kind of the privacy part. Then you also have the part where it is really linking quantum computers together. So as you might know, it is really hard to build a quantum computer. And this is for an important reason, that is just really hard to make good qubits, but especially good qubits on a big scale. So it's much easier to make a single qubit that can do really well, but to make millions of them and put them all on a single chip that all perform really well is really hard. So the idea is also that you maybe, if you have a quantum network, you can link multiple quantum computers together. This is another way to scale up and to make quantum computers bigger. And lastly, I think, and for me, this is maybe the most interesting application, is to use it as a scientific tool. So, for example, there are ideas how you can use such a quantum internet to connect different atomic clocks and thereby increase the precision by which they're synchronized. And if you increase the synchronization, you can, for example, increase the accuracy of GPS signals. But also, for example, if you want to know where gravitational waves came from, it's really important that you have synchronization of clocks over bigger distances to connect different detectors of gravitational waves. And if you have really good timekeeping, then you can more reliably say where these waves came from. So I think this is a really cool concept. And for example, there's also an idea how you can use a quantum internet to increase the baselines of optical telescopes and be able to increase the resolution of your telescopes on Earth. So I think these are really cool ideas where you use such a quantum internet as a scientific tool to investigate new science, especially because all the concepts we are using are built on such a lot of fundamental other research. So these are the three kind of reasons why you would like to have a quantum internet. And I think there might also be quite a few unknown applications that nobody has thought of yet. At least that's what I hope, of course. So if we then kind of go to the next slide, then you can see a bit scaled down version from this artist impression. This is our artist impression of our own network. So, of course, to industry standards, we called our nodes Alice, Bob, and Charlie. And what you can see is that Alice and Bob are connected by a fiber, and Bob and Charlie are connected by a fiber. This is this yellow line. And those can be used to make these quantum links. And these quantum links are something which is entanglement, and this is depicted by this wiggly blue line. And entanglement is something where you really share where two particles really share some common information or common behavior. So, and you can use this quantum entanglement to send information. So we'll go a bit through how this works, not all the math, because I think it can get really mathy, but the idea how you would use such a quantum link to send information. But I think for people that are not so familiar with the concept of entanglement, I always like to think of entanglement like if you both have a coin and this coin is a quantum coin, so you can spin it and it falls either on heads and tails, right? If you do a measurement in quantum, it can be in a superposition before, but once it falls down, once you measure it, it has to choose. So if we share a quantum coin and we both throw our quantum coin up, then it always falls on the same side. And I think this is an important kind of, you can have your own picture, and I think all kind of analogies break down at some point, but I really like the quantum coin one because it, I think, gives some insights on how such a thing kind of works. So there's kind of a one coin can't influence the other coin, right? If you have a entangled pair of coins and you have them both spinning, you can't decide whether they're gonna fall on heads or tails. But only once you look at the correlations between the two, you see that they always fall on the same side. So there's kind of, you can't influence one coin by the other, but you will see that they always do the same thing. And this is an important part. So there's nothing that kind of breaks causality. You can't transmit information faster than light because you can't use this entanglement to directly send information from one point to the other, but you can use these correlations between two distant points to send information. Okay. Yeah. So if somebody has a question, let me know. I'm keeping an eye on the chat. But
I have a quick question, if that's okay,
yeah.
please.
Oh, sure.
I'm trying to get my head around what you're saying. How you can't affect, like, if two coins flipping, that they are connected. You can't make them do anything, but you can work on the prediction that they are working together in some way. Is that right?
Yeah, maybe. So maybe if if we make it more concrete. So say we share a coin, right? We share an entangled pair of coins. So we both have them spinning right now, and I try to make sure whether I want an Americano or an espresso to you, right? There is no way for me to kind of flip my coin in a way or do something to my coin that I can transmit information to you directly, right? The only thing I can do is to measure my coin, so to kind of smash it on the table. And if I see heads, I know you also see heads, but for you, heads has no meaning yet. Only once I kind of send you a message and say, okay, if you see heads, it means I want an espresso. You know that you have to order an espresso. So kind of, I knew you would see heads, but that was only a chance or a statistical game. Only once I measured it, I knew what you would see, but there is no information transmission because you can't interpret it yet. Only once I sent you kind of a decoding message, you can have access to this information. And this is, I think, what is really important to understand about all this quantum communication. This is really what is saving kind of the not transmitting information faster than light principle. If it was possible to extract information, then you could travel back in time and kind of whole of relativity would break down. But that's not the case. Is it maybe clearer, Jamie?
The one thing, I don't want to hold back anything
Oh, sure.
on my not understanding this, but one thing I'm not really getting is so if you're flipping the coin and you know why you're flipping the coin and that was for the espresso or whatever, and then you then know that as I'm flipping a coin, I'm receiving heads just like you. The only way that has any meaning is if I get some kind of metadata packet explaining what the meaning of the heads is. What would the point in flipping the coin be then? Because isn't the internet just simply sending this data already? So, I'm not sure. Yeah,
because kind of you can see this flipping the coin as the key, the encryption key, right? So nobody else will know whether you ordered an espresso or what was it, an americano for me, because they don't have access to our chance process, our entanglement. Only you and I know that we flipped heads, but that's a chance process of 50%. And so if we extract this a bit and you do this really more rigorous with many more attempts, then at some point you can generate like 1,000 or 2,000 bit key string, and you can completely encrypt your information without somebody being able to extract the key.
Oh, okay. This is becoming a bit clearer to me now. Yep, because if you're only in control of if we're both flipping together, and you're then telling me what significance it is to your coin, to my coin, but it's coming directly to me, then there's no way that could be intercepted or decoded or anything like that. Yeah.
Exactly.
Something like,
Yeah.
right. Thank you very much for your time. Thank you for answering my question.
So this is, I think, an important concept, and this is when you're using quantum networks for quantum encryption. But we can maybe later look in how you can also use it to send information, and that's where the whole teleportation comes in. So on slide 3, we have our quantum network. We have 3 nodes, 3 of these quantum nodes. And I think it's nice to point out that this is like the first time in the world that a 3-node network was built. So before, many people have built, or quite a few people have built like a 2-node connection, but scaling up to 3 is quite a bit more complicated, because the rate of your experiment and the fidelity or the quality of your experiment needs to be above a certain threshold to be able to scale up from 2 to 3 nodes. So in the picture, you can see that we have kind of these purple purple arrows, and these are spins. So we encode our information in the spin of particles, and the spin is a quantum mechanical phenomena, but to make it a bit more classical, you can think of, is it spinning to the left or the right? Or you can think of like a little magnet. I think that's maybe the most intuitive. And the magnet is pointing up or down, or maybe to the side, and then it is in a superposition, and it's partially pointing up and partially pointing down. So all the purple arrows are our communication qubits. We use them to make entanglement and to communicate between the nodes. And then we also have a yellow qubit. This is our memory qubit, and we can store quantum information in there. And then we have these optical fibers, these yellow lines, to make entanglement. And the blue lines are kind of an artist impression of the entanglement that can happen between the nodes. So I'll go a bit deeper in how we make these things. So if you go to slide 4, you can see how our communication qubit looks like. So as I said before, if you want to store quantum information, just like if you want to store classical information, you need some encoding scheme. And for a classical bit, this might be, for example, the orientation of a current in a circuit, or the presence of a charge being somewhere or not, or a light being on or not. And for our quantum system, we use the orientation of the spin of our qubit. So on the right, you can see again this purple arrow, which is the spin of an electron. But we need to trap the electron somewhere, and we do this in diamonds. So diamonds are lattice of carbon atoms, and this is depicted with these black dots. And if there's like a defect in the lattice, an electron can get trapped in there. And we specifically make use of the nitrogen vacancy center. So there are two kind of missing carbon atoms. One is completely missing and the other is replaced by a nitrogen atom. That's the green ball in the picture. And this electron has a spin trapped in this hole, and this spin we use as our communication qubit. And then I think, at least for me, when I started my master project, the question would be, how do you read out the quantum state of such a system, right? How can you determine whether the spin was up or down? And we do this by using lasers, because these defects are called color centers, and that is because they were kind of discovered to color these materials. So, for example, if you have a diamond full of nitrogen vacancy centers, it will be a red diamond, because kind of the NV center can emit red light and absorb red light. And we use this to read out the spin state, because people found out that if it's pointing in the up direction, it absorbs and emits a slightly different color of red than if it's in the down state. So what you can do, which trick you can do, is if you shine in a laser that's, for example, resonant, so which can excite the zero state, you excite it to the excited state, just like you can think of how an atom could be excited to an excited state. And if the light falls down, then you can detect this light, right? So what we do if we want to know the state of our NV center, we shine in a red laser that's exactly on resonance with this transition of the zero state to the excited state. And if we see light coming back, that means that our NV center is in the zero state. If it stays dark, we know the NV center was not on resonance with the laser, and so it should be in the one state. And in this way, we can detect the qubit state. And we can use another color of red to initialize our state in the zero state. And we can use microwave pulses to change between 0 and 1. So if we put a pulse of microwave frequency or microwave of microwaves next to the NV center, it can change from 0 to 1 and from 1 to 0, or we can put it in a superposition, so partially 1, partially 0. And on the right side, on the bottom, you can see two pictures. The grayish one is one of the diamond, and you can see this kind of this semi-dome. This we call a solid emerging lens, and this is to enhance the collection of the light coming from the NV center, because this NV center is super tiny, small. You want to collect all the light there is, and these LiDAR lines are a gauge and a strip line for changing the electric field and for applying microwaves to it. And the bottom right picture, the bluish picture, is kind of a microscope picture of this device. You can see, if you look good, you can see the dome, and you can see this bright spot in the middle, and that's our NV center. So this is a single electron that you're looking at, right? This is exactly the picture that is above. There's only one single electron that's emitting this light, and we can see this electron being there in the middle of our solid emerging lens. So what you can see here is we have a method to read out our electron. We have a method to reset our electron, also by laser light, and we have a method to control our qubit, right, between 0 and 1 using microwaves. And there's a last thing you can do. If you put your electron in a superposition, so 50% 0, 50% 1, and you then apply a short readout pulse, you will get light back if you're in the 0 state, but you won't get light out if you're in the 1 state. So what happens then is that there will be a photon emitted, but depending on the spin state, right? There is a 50% chance that you were in the 0 state and you emitted the photon, or there's a 50% chance that you are in the 1 state and you didn't emit a photon. And this is exactly what entanglement is, right? So we have now, if we do this experiment, so we put our NV center in a superposition of 0 and 1, we apply a short readout pulse, we can entangle the spin state of our NV center with a photon. And the photon is then encoded in partially being there and partially not being there. So either 0 and there was a photon, or 1 and there was no photon. And that's our entanglement, and we call this spin photon entanglement. And this spin photon entanglement is used to kind of connect different centers together. I will come how we do there in 2 slides. So
quick question.
Yeah, sure.
If you can control the qubit, then you are essentially sending information, right?
No. So how do you mean that?
Well, if you can control a qubit on one end and make it up or down, then you can read it on the other side. So that is sending information, is it not?
No, because it's always really tricky. If you have the feeling there's information to be sent, then there is some trick or something tricking you. So what it is here, say we share information. If we go back to this coin example, if we have an entangled pair of coins, and for example, what I can do with this microwave pulse is that I can say, okay, if I was in 0, I will be in 1, and if I am in 1, I will be in 0. But that's the same as flipping your coin, right? You will change heads to tails and tails to heads. But if we have an entangled pair, and in quantum world, we are able to apply this operation to a spinning coin. So I say, okay, I change my coin, I flip it 1 extra time. Then if we slam our coins on the table and I see tails, I know you will have heads because I flip my coin 180 degrees. But still there's no information sent because I only changed the statistics. I changed kind of how we correlate. Before we correlated that we always had the same thing, and after this pulse, I changed it to always anti-correlate. But still I can't send information to you. Does this make sense?
Well, I don't know. I think when you use the word control, like you can control it, I thought the qubits matched, but I guess not.
Yeah, so I can control it, but once it's entangled, I can't initialize it again, because if I initialize it, I remove the entanglement. So if our coins are spinning and I kind of reset my own coin, then it won't change the state of yours. It just I just reset my coin, right? So I'm not able to prepare it while the entanglement is still there.
Okay, and then what do? You have to re-entangle somehow?
Exactly. So what if we want to make entanglement? Maybe I can come back to your question if I explain how we make entanglement between 2 nodes, because then I think it makes more sense. Yeah?
Okay, thank you.
Okay, so we now have our communication qubit. And by the way, I really like these questions in between, because I think it is such an abstract concept, all these kind of quantum effects and entanglement, that I think it's really helpful to have some questions in between. So we now have our communication qubit, but we also still need some way to store our information. And how we do this is we make use of something which is just around. So if you go to slide 5, you can see that, again, I depicted this nitrogen vacancy center. But now there are also these yellow arrows around. And what these yellow arrows are is carbon-13. So normally carbon is carbon-12, the isotope carbon-12. But it can have an extra neutron, and then it's carbon-13. And carbon-13 has a nuclear spin, whereas carbon-12 has no nuclear spin. And 1% of these carbons are carbon-13. So you have kind of this whole lattice, and just once in a while, there is a carbon-13 in this lattice. And what is interesting is there is kind of a connection or an interaction between this carbon-13 and the electron spin, which is called the dipolar interaction between two spins. You can see it if you think about these spins as small magnets. If you hold two magnets close to each other, you feel that they are interacting. And the same thing happens between our electron spin and the nuclear spin. And what we can do now is that we can use this electron spin. If we flip it in the right kind of order, and we do it at the right frequency, we can change the state of our nuclear spin. And so we can use our nuclear spin to store the quantum information we had on the electron spin. So for example, if we have entanglement on the electron spin, we can move it to the carbon spin, and in this way free up our electron spin again. And colleagues of us have shown that you can do this for 8 of these nuclear spins, or 9, including the green one. And thereby, so it is not that you have just one of these memory qubits around, but you have many more of them. So it is quite interesting, I think, that nature just happens to have 1% carbon-13, and this is just there in the lattice. And normally it's a bit annoying because all these little magnets are influencing our system, but you can also use them. And I think for us, for our experiments, these memory qubits are really important, so that you also have a way to store quantum information for longer. Okay, now we come, I think, to the meat of the whole story. This is namely, how do you make entanglement? So we can forget about the memory qubits for a second and just focus on these communication qubits. So if you go to slide 6, you can see how we make entanglement. So what we do is we prepare both. So we take 2 completely separate setups with their own diamonds and their own NV centers. We prepare both NV centers in a superposition, and then we send to both NV centers a short readout pulse. And this readout pulse entangles then the electron spin with the photon. So again, what we discussed with the communication qubit, if the electron spin is up, then then there is a photon. So sorry, if the electron spin is in state 0, then there is a photon, and if the electron spin is in 1, then there is no photon. And this is kind of indicated with this wiggly line, which is a photon, so a particle of light, partially being there, partially not being there. And this happens on 2 setups. And so far we just have 2 times entanglement between a spin and a photon and a spin and a photon. But then we apply a trick. We have a partially transmitting mirror in between. So this mirror is 50% reflective. So if you shine light on it, half of the light will go through and half of the light is reflected. And if we then let these photons exactly hit at the same point the mirror, and we put 2 detectors after this mirror, if one of these detectors clicks or detects a photon, we know that one of the spins should be in the up state. And we just detected 1 photon, so the other one should be in the down state. And then you think, so what? But the interesting thing is, we don't know from which setup the photon came, right? Because this partially reflecting mirror has made it in such a way that there's a 50% chance that it came from the left or 50% chance that it came from the right. And what now happens is we call that it removed the which path information. So kind of it's not known anymore whether it came to the left and the right. And it's not just the case that it's not known anymore to us, but it kind of nature also forgot. And the only way to resolve this is to put the electrons in a superposition, right? And the superposition is then kind of the state of these two electrons that allow this, which is that one is in the zero state and one is in the one state, or the other way around. So we have now kind of a situation where there's a 50% chance of having 0, 1, and a 50% of having 1, 0, if we compare the two. So it's kind of analogous to having these coins which are spinning, and you know that the moment you slam them down on the table, they will always show the opposite heads or tails. Right? So this is the way we create entanglement between two spins. So we put our electrons in a superposition, then we make spin-photon entanglement, then we let these photons, which are partially there, partially not there, fall on a partially reflecting mirror. And by detecting a photon, kind of nature forgot which setup emitted the photon, and by this we entangle the electrons. So this is, I think, kind of the magic in our whole experiment, and kind of a tool we will use to teleport the information later. So maybe if there are questions, I'm happy to try to make it clearer, but I'm not sure if there are.
So my question here is that I'm thinking the key here is the quantum entanglement, which for me is a bit sticky in my head. But so the idea is then that you can using the coins again, you make a quantum connection, a quantum entanglement between my coin and your coin, right? So that you can now predict that they are connected, and you can rely on that, right?
Yeah.
And so then, because only my coin and your coin are quantumly entangled and nobody else's is, that means what you were talking about before with nobody else could intercept it or know what it meant or anything like this, yeah? Does this then mean that that when you're using the quantum entanglement, you're essentially not relying on, it's almost like a quantum network, not the way the internet works, but it's taking advantage of the very nature of quantum physics to actually allow transmission of information. Is it something like that? I'm sorry, I'm doing my best here, but this is quite.
No, it's really tricky, right? So what we want is to have this entanglement, and so this entangled link, what we can do with it is we can send information. I'll explain this in the next slide, but we can use such a link. If you now think of this entanglement as being kind of a quantum link between these 2 points, we can use this link later on to send quantum information from one side to the other, right? So indeed, this kind of is, you can see this quantum entanglement in this slide 6 as kind of a building block of a quantum network. We all the links in our network should be these entangled links, these wiggly lines. And we use kind of the photons and these partially transmitted mirror to make entanglement between 2 distant points. So to make entanglement, you should have an interaction between kind of your the 2 things you want to entangle. So in principle, we could also bring the 2 spins really close to each other and then take them apart again, but that's not at this moment at least technical feasible. And also for later applications, right? If you have your nodes 100 kilometers away, it is not practical to bring your nodes together and then get them out again to use it for quantum communication. So then we use these particles of light as kind of a messenger qubit. They travel the distance, and they make sure that kind of the 2 spins come together, and in this way can make entanglement. But so they don't come physically together, but the photon that they are entangled with come together. Does it make a bit of sense?
Yeah, if I may also add and ask at the same time. So, as far as I understood, additionally, what makes it safe is that as soon as somebody tries to interfere, you would detect that right away, because then, you don't have the entanglement anymore, right? So, as soon as somebody tries to intercept or spy on this information, then you would immediately record that, right?
Yeah, that's a good addition. So if, for example, if somebody would kind of try to intercept one of these photons that are traveling and try to read out that you're trying to make entanglement, you will never make perfect entanglement. And you can just, so it kind of interrupts this whole system. The photons won't come in at the mirror at exactly the same time. They will, you can see afterwards that it's not that somebody was listening in. So if you make in how kind of real world quantum encryption protocols work, is that you make entanglement like maybe a couple of thousand times, and you check once in a while whether you're really making entanglement. And you can just say, hey, what did you have? I had heads. Oh, I also had heads. Okay, apparently it works. And if you make the statistics well enough and you see that you always make entanglement, you know for sure that nobody can be tampering with your photons or you're trying to make entanglement. So if you see that you have entanglement, you know that nobody is trying to eavesdrop on you. But that's a good addition indeed.
One other question I've got at the moment, and this is what I'm trying to get it set in my head, is I think I'm getting my head around what you're doing with the quantum entanglement, right? Um, when you're quantumly entangling something, is that something that's like literally outside of any hardware that we're giving it, or is this requiring the hardware? Like, are you entangling something, and then if there's no like physical network anymore, no cables to connect data connecting, is that quantum entanglement still there, or is this like, is there artificial network of cables and lights and everything like that maintaining this entanglement? I don't know if that's even a stupid question.
No, that's a really good question. So as you can see, you need these photons to arrive at the same point, right? So to make entanglement, you need optical fibers to connect your nodes. But once you have entanglement, it stays there. Even if you would cut your cables and you could cut all the cables, the entanglement would still stay there. The cables are there to make entanglement, but it's not necessary to keep the entanglement there. The only problem is that all quantum states are really fragile, and so we can maybe keep our electrons alive to maybe 0.1 seconds or so. If we really push, we can get it maybe to a second, but that's kind of it. So you should cut them then really fast and see whether you still have entanglement, because kind of the quantum states are degrading. But that's not because of the fibers. The fibers could in principle be gone. But I think it's good to stress that this entanglement is not like a thing that will always be there. In the same way as the coins that are spinning, once you kind of slam them on the table, you have used this round of entanglement and you need to make it again. So a bit in the same way as with the current internet, it's not as if once you send a single bit over the internet, you can send bits for the rest of your life, right? Each bit has to be sent again. And that's the same for entanglement. Each time you use this entanglement for either using it as a quantum link to send quantum information, or for example, to make a bit in your key for quantum cryptography, you have to remake it. So in this sense, you need the cables to stay there, but from a quantum mechanical perspective, you could remove the cables and the quantum entanglement could still be there.
Interesting then. So that's then saying that the equipment is continually why it's there then is to continually reinitialize the connection between two nodes. That's essentially why it's there. But the quantum entangled nodes themselves are what's transferring the information, whereas the apparatus is only just reconnecting the quantumly entangled link. Is that right?
Yeah, exactly. And so now if we have two setups, kind of we can make entanglement around 10 times per second, so 10 hertz. If you compare this to the like gigabit speeds of the current quantum net or the current internet, it's not fast, but you can in the end, right? I think there are also already experiments where you have kilohertz entanglement generation. So I would not be surprised if this just continues. I don't know kind of what is the upper limit, how fast you can make entanglement, but or how often you can make entanglement. But indeed, this is really, thanks for the question. That was a really good insight. So maybe we can go to slide 7, which is the experiment we performed. So what we did is we used all this trickery I've explained so far to send information over our quantum network. So if you look in the slide, you can see we have Alice, Bob, and Charlie depicted as 3 rows here. And the goal of our whole experiment is to send a qubit from Charlie to Alice, right? And maybe we can think a bit on how this is done usual, right, in a classical network. If you want to send information or a bit from one point to the other, what you do is you copy the bit and you send it a couple of times, or you use error correction, or you use at least a way of copying your information and then sending it a couple of times if you want to be sure that it arrives at Alice. Because if you would send it once, for example, if you send it as a pulse through a coax cable or a pulse light through a fiber, there's a probability that it gets lost, or that you have noise and it gets misinterpreted. In the end, you want kind of to be sure that the right state arrived at the other side. But there is a problem if you want to use this exact same tactic to send quantum information. Because in quantum mechanics, there's a so-called no cloning theorem, which says that if you have a quantum state and you want to copy it, that's not possible. So there's no way to copy quantum information. And that's important to realize here. So if Charlie wants to send the state to Alice, but just sends this, for example, encoded in a photon, maybe we now encode it in the polarization. So we say horizontal polarization is 0, vertical polarization is 1. And we send our precious qubit through a fiber. The fiber has losses, and it can be that our qubit just get lost on the way. But there's no way to retrieve it, right? Because of this no cloning theorem, qubits can't be copied. So then you just lost your quantum information. So we have to come up with a new trick, and this trick is called quantum teleportation. So we can use an entangled link, for example, the one that we made in 6, to send our qubit. What you then do is you, for example, in step 4, you can see, I can talk you through the list. Maybe that's clearer, but what you do in quantum teleportation is you use this entangled link and then send the qubit over this link to make sure that it arrives at the other end, right? So you can do quantum teleportation with 100% success rate, whereas sending the qubit directly would never have 100% success rate. So what we did in our experiment is we made entanglement between Alice and Charlie. That's kind of the end goal, and used this entanglement to send information between Charlie and Alice. However, the problem was that there's no fiber between Alice and Charlie, right? This is kind of imitating a real world situation. Kind of, if we would have a quantum internet, you're not connected, you don't have a direct link to everybody. So you sometimes need to send information through somebody else. And that, in this case, that is Bob. So what we did in our experiment, we first made entanglement between Alice and Bob, right? This is step 1. So this is exactly what I just explained in 6. We make entanglement between Alice and Bob. What we then do is we store our quantum state on the nuclear spin, so on this yellow spin. That's step 2. This is called a swap. So you swap your information to the memory. What we did in this case is we kind of freed up our communication electron or our communication qubit to make another entanglement. So what we then did is we made entanglement between Bob and Charlie. And what you now can see is we have entanglement between Alice and Bob and Charlie. And what you can do now, and this is, I think, mind-blowing, is you can teleport the state on the memory qubit of Bob to Charlie, right? So you can use the entanglement between Bob and Charlie to send your qubit, your memory qubit of Bob, to Charlie. And if you now look, right, if you would kind of drag this line along the like dashed line, you would see that the entanglement between Alice and Bob ends up from Alice to Charlie, right? In step 5, you see there's entanglement between Alice and Charlie. So in step 4, we teleport the entangled state of Bob to Charlie. And how we do this is we do a measurement on the 2 qubits of Bob. We ask, for example, is one of you in the 0 state? It has to be a joint measurement, so therefore also you see this eye looking at the 2 qubits. And we need to send this information over a classical network, so for example the internet, to Charlie, because Charlie ended up with a encoded version of the qubit. So if you send a qubit over an entangled link, it ends up encrypted at the other side, right? Otherwise, this is like all the things we've spoken so far. Otherwise, you would be able to send information faster than light. So you still have to send a message with the measurement outcome from Bob to Charlie to kind of make sure that you can decrypt the teleported state. But if you now, so there are lots of details involved, but if you now zoom out a bit and you just accept that an entangled link can be used to teleport a state, then what happens in 4 is you have entanglement between Alice and Bob and between Bob and Charlie, and you teleport, so you move the state from the yellow qubit in Bob to Charlie. And so you end up at step 5, where you have entanglement between Alice and Charlie. So kind of, I can understand that all these individual steps are really weird because it is quantum mechanics in the end. But I think if you start to look at it from kind of a zoomed out perspective and accept that you can teleport information over an entangled link and that you can move this quantum state from one place to the other, you can see that you end up at step 5. The trick we then did is we again stored the situation, the state in the memory qubit of Charlie, right? We again did a swap gate, but now on Charlie, and we freed up the electron. So you can see that in step 6, we made entanglement between Alice and the memory of Charlie. And what we then did is we prepared the qubit we wanted to teleport on the electron, and we sent it to Alice. So we did this whole kind of this 7-step process to arrive at our goal of sending qubit from Charlie to Alice. That's kind of the teleportation. So that explains all the things in our experiment. So we have a 3-node network, and we send information between the non-neighboring nodes in this network. Does somebody has some questions about it? I would be surprised if not, but
At the moment, I'm just trying to take in everything, but if anybody else has any questions, feel free to let us know. I think we're good for now, Doctor, please.
Okay, great. And then the last thing what we did is kind of a bit an insight how you can measure this is, so we prepared our qubit in 6 different directions, in the z direction, in the minus z direction. So this is 0 and 1, but you can also do it, you can rotate your little spin in the x direction or the y direction. And we looked at how well we can teleport these states. So that's what you see here. The teleported state fidelity says like how much the state that arrived at Alice looked like the state that we tried to send. So this is around like 70%. But there's an important thing here, that there's a dashed line at 2/3, and 2/3 is kind of what you can still explain from classical physics. This is kind of, I can cheat my way through 2/3, but everything above 2/3 requires really teleportation of your state. So what we were able to show is that the average of the quality of our teleportation was above the bound that can still be explained from classical physics, and shows that we really showed teleportation in our network, and not just some happy accident. Right? So this is how we were sure that we are also really teleporting our state. Yeah. So then that leaves me with thanking the group in figure 9. I think we have a really nice group in Delft, all working on closely related subjects. So yeah, this was my presentation. I'm happy for another 15 minutes or so answer any questions you have.
Well, thank you very much for your talk, Katerina. I actually have a question just now, and I'm sorry. Like I said, you've given me a lot, and there's a lot to chew over here. But when you say teleportation, then, right, is what does that mean exactly? Because that's like nothing's being transferred any physical way. Is that like one thing being instantly received somewhere else with no intervening distance, except for through the quantum entanglement? Is that right? Or I'm trying to understand the teleportation part.
Yeah, so I think if you compare it to like Star Trek teleportation, then the thing that's missing there is kind of indeed the matter that's being transported, because it's only information that's being transported here. And kind of you always need to send some classical message with your measurement outcomes to the end node, in just the same way as we just discussed with you, that if I try to tell you whether I want an espresso or an americano or whatever, I always still need to send you a message how to interpret our correlations, and it's the same with this teleportation. But still, I think so these are the two things that are different from kind of the sci-fi teleportation. But I think there are two things that are interesting to notice here. So, for example, if you want to teleport an electron from one place to another, then you could say that we haven't transported the electron. But on the other hand, all electrons are exactly the same. There's no way to tell two electrons apart. So in principle, you could also argue that if you transmitted all the quantum information from one electron to the other, there's no way to tell if you would have these two electrons next to each other that you didn't move the electron. So I think that's kind of more philosophical part of it. But you're completely right. So the electron was never moved, but you really kind of only moved the information. And it was not instantaneous, or at least not, you still needed to send this message. And again, that's really important, right? Because if you didn't have to send this message afterwards, that would mean you were able to send information faster than light, and that would mean relativity would break down and you were able to travel back in time. So I think kind of there's not, so this is the closest thing to sci-fi teleportation we're ever gonna get, I'm afraid or happy about.
At least for now.
That's absolutely fascinating. And one of the things I was wondering, do you think that this could lead to some kind of thing where we could have communication between people without having a massive network, global network around the world? Do you think, like, if I had a little, I don't know, like a little station in my living room that sort of like can entangle bits together, could I then send you something, sort of wirelessly, I suppose, the best word I can think of to say, but there's no fundamental internet. I'm not paying anything to an ISP or anything like that. I've just got this little machine. It quantum entangles stuff to you, and then I send the stuff to you. Is that kind of thing ever going to be feasible, or does the thing functionally not work that way?
I think not, because you need the infrastructure to send these photons around, right? So whether that's through a glass fiber or via a telescope or a satellite, or right, you always need to send this quantum information, so these photons to make entanglement. And only once that's made, you can use this entanglement. But you always will need to send around these photons for the creation of the entanglement.
Okay, so the photons then entangling them together is what allows this to actually happen. So that means then could we then have an internet then that has no real limit to its speed then, like downloading anything from a sound file to like a gigabytes of information could all happen like almost instantly?
And so I would be really surprised if a quantum internet would be faster than a classical internet. It's more that you enhance the capabilities, but if it comes down to like just raw speed, I would be really surprised if a quantum internet would be faster than a classical internet, because you need to take care of so many more things and it's so much more complicated, that I think in raw speed a classical internet will be faster. So how we as a community, I think, envision a quantum internet is not a replacement of the current internet, but more a kind of an addition to it, right? So for a quantum internet to work, you also need to be able to send classical information for all these encoding, communication, and there are just also things that are just uh, uh, not really quantum information, or that are not needed of this encryption. So I think how you should envision it is having two separate or two parallel systems that are closely linked, but one won't replace the other.
Yeah, thank you so much.
Interesting. Thank you. Thank you.
And I would like to give Ali and Dr. Shah and Gilbert opportunity to ask a question, if that's okay with you, Hans, if you still have
Yeah,
a few
sure.
minutes.
Yeah.
Perfect. Thank you so much. So, yeah, Dr. Shah and then Ali, please go ahead.
Thank you so much, Hans. That was a fascinating, presentation. My question from you is about putting the system on a ground energy or close to the ground energy. Do you have any explanation around that? Because we know that is gonna give us the final state for the entire system when we just put the system close to the ground energy. I was just wondering, based upon your information, do you have any further information around that?
Sorry, so you mean what the ground state of our quantum system is,
No,
or and how we get
if you
there?
if you wanna, yes, you explain about all of those, I mean, features, and I was just wondering when we put the system in a ground energy, what's gonna happen to the, I mean, qubits and the information and data.
So sorry, so I'm trying to understand what you mean with the ground state. You mean in
Tanglement,
the
you
low state
can,
of the
yes, you can just talk about the tanglement and how it might be different, because I mean there is some description about the different feature of the, I mean, because we are talking about the quantum computers, right, and about the tanglement. When some of the scientists put that close to the ground state, there's some changes happen, and I was just wondering maybe you have further information that you can share with us.
Yeah, so I think there's not so much what changes because so our system is really well isolated. Um, so it even kind of you the entanglement doesn't work really at room temperature, but you can at room temperature this kind of qubit still works, but you just can't make the spin photon entanglement, but the qubit is still working. So this means that our system is really well isolated from the environment and that it is always really staying in the ground state of the energy structure. And making this entanglement, I think, doesn't really change the dynamics of the system in this way. It's still it's still mostly influenced by the effect of single nodes in this way. I'm not sure whether I'm answering your question, but
Yeah. I mean, if we want to just open the, I mean, section is gonna be long. So thank you so much for your answer.
yeah.
Ali, you want to go
Mhm.
ahead and ask your question?
Sure. Hans, thanks a lot for your amazing talk. When you were talking about Alice Charlie, I recalled your paper, your Nature paper I read before. I have a couple of questions. The first one is about the dimensionality effect. If you're gonna move from 2 to n, and in n dimensions, do you think we still can form a coherent superposition to maintain the teleportation intact, or
Yeah, I think
what do you think about that?
yeah, thank you. That's a good question. So, um, I think the concept, what is important here is how well you are able to store your state compared to the speed at which you can make entanglement. So maybe if we go back to the analogy with the coins, right? If Alice and Bob were able to make entanglement, so they have these spinning coins, then they swap to make Bob and Charlie making entanglement, right? But the problem is you slowly have decoherence in your system. So slowly kind of how you can maybe think of this is that your coins are slowly start to wobble and slowly already out of themselves start to fall down on the table. So kind of your entanglement is degrading and you have to make entanglement between Bob and Charlie fast enough before the entanglement between Alice and Bob is degraded too much or it's gone. So what we do in our experiment is we make entanglement between Alice and Bob. And we then try 1,000 times between Bob and Charlie to make entanglement. If we don't succeed within these 1,000 times, we start all over again. We start again with trying to make fresh entanglement between Alice and Bob, and then again we try to make within 1,000 times entanglement between Bob and Charlie. If we fail, again we stop the experiment, we go back and we make fresh entanglement between Alice and Bob. And we repeat this so often. So on average, we kind of can make entanglement once every 50,000 times. So it takes a while, but at some point we'll just be lucky and make entanglement between Bob and Charlie within these 1,000 attempts, and then we can continue with our whole experiment. But there's some statistical game in this, and the problem with scaling up, at least with the parameters we have currently in our system, is that if you have many more of these things that just need to happen at the same time, then it just becomes really unlikely that they all happen at the same time. So with our current system, kind of 3 is the most we can scale up. But if you can make entanglement faster or you can store it better, then you can scale up to 4, 5, 6 nodes. But to go really to like tens of nodes, just the performance of the individual nodes need to improve a lot to kind of don't get hit by the statistical game so much. Is this explaining your question?
Yeah. Thanks a lot for your great answer. I know it's one of the biggest challenges in the field. And my second question is also one of the challenging, issues we are facing. So, what do you think about overcoming the issues like coming from the propagation loss of light, and also atomic coherence lifetime? These issues can be raised from the classic protocol. I would like to know your idea or your solution in this area as well.
Yeah, so I think for the NV center, at least, kind of the coherence times are maybe milliseconds. So I think that's not really the problem, because in this time that's easily long enough to kind of store states while your photons are traveling and say that you have entanglement. So I think for the NV center, at least, the coherence times of the spins are not a problem. The losses are a really big problem. So we're now a couple of meters apart. So most of our losses come from the inefficiency in collecting the light with a microscope objective, and some internal efficiencies of the NV center. But if you go over larger distances, the losses are insane for red light. So we have also a sub-project in our group working on making entanglement over tens of kilometers between 2 cities in the Netherlands using this system. But what they do is they use a trick. They transfer the photons from red to the telecom band, so from 637 nanometers to 1550 nanometers. And what you do by this is you increase a bit of the losses, because this conversion process is maybe only 15% efficient. But then once you send them through a fiber, the losses are so much less, because this is really the part where the losses are lowest for transmitting them to fiber. So kind of there is a trick to this, that if you're not using telecom light, you can use nonlinear optics to get your photons into the telecom band and then send them through a fiber. However, for NV center, this is still slow, but there are other systems coming, right, that have higher, that are brighter and send out more light. So then we can speed up. But yeah, this is, I think, this will be one of the biggest challenges in the field of quantum networks, to overcome all these losses and still make your system fast enough to operate.
Okay, thanks a lot for your answer, and it was a great pleasure, to hear you, and thanks again.
Thank you.
Yeah, I have a quick question. So could you maybe have 2 different lights send always out 2 different lights, one that comes faster but maybe loses a lot on the way, but then you have the slow one coming in next to kind of confirm the information process? Or would it be too expensive and too extensive to have basically 2 light signals one dirty one that comes first, and then the accurate one that comes like, I don't know, a few milliseconds after.
Yeah, thank you. So, so I think the speed of the light is not the problem because they all travel at the speed of light, and maybe that's 2/3 of the speed of light in the fiber. But it's more the losses on the way. So, for red, it's 6 dB per kilometer. That means, so maybe kilometer is not the best intuitive measure for you, but it means like 250 meters, half of your light is gone. Whereas for telecom light, this is 0.2 dB. So that means that you need 15 kilometers to lose half of your light. So that's a factor of 60 difference in the amount of losses you have. So it's not so much the speed at which light is traveling, but more the losses you have on the way and how likely it is that you lose your light.
Yeah, okay, I understand. So could you would it be too expensive to send a lot and then calculate the overlap probability basically? So, it doesn't matter if you lost, but if you send 100 times the same thing, or probably, I don't know, 1,000
No,
times.
so you can at each try you can only send a single photon, because if you would send 2 photons and you would lose one, that means that kind of nature measured your entanglement, and then your entanglement is gone. So right, so if you can't have a lot of light traveling, there's always only a single photon traveling through the fiber at a single moment. So you can't increase it because of the no cloning theorem. There's no way to copy your signal more often. So this is a trick that you can use for classical networks, but that doesn't work for quantum networks. So the only trick you can do for quantum networks is try faster in repetition rate. So you try, if it gets lost, you try again. If it gets lost, you try again. But there's no way you can boost your signal for a single try.
Okay, I see. And then there was a question in the chat. I know we kind of partially answered it already, like if teleportation one day would work for our bodies, and you kind of said no. But could we, if let's say we have infinite amount of data we can send, could we send the metadata of our bodies basically? So
I think there's no so kind of that's really a more, I think, a philosophical question, but I think in principle, at least how we understand nature right now, kind of in the end everything boils down to being quantum information. So probably it's possible, but I think I would not be surprised if in the end the teleportation is not a problem, but that it is more having an efficient readout and rebuilder of your body, right? Because then what you need to do is to scan your whole body without losing the quantum information while doing that, breaking down your whole body, and then sending this. I think if we're able to do the first step, then I think sending all the quantum information will be the easy part. So kind of the teleportation part will be easier than reading out all the quantum information of your body. And then I think maybe even more tricky will be to rebuild your whole body while while putting all this quantum information in. So kind of the reader and writer part of the problem, including all the 3D printing that needs to happen on the other side, I think are more challenging than the teleportation part.
yeah, I'm imagining the 3D printer and the okay. Thank you so much. Maybe we should try with I don't know, some ants first and some mosquitoes.
Yeah, that sounds like a better better starting point, but still probably extremely challenging.
It would be fun though to send all the mosquitoes to Mars, so they have the mosquito problem, and there all that money and still mosquitoes. No, I'm kidding. Sorry. Okay, yeah. Does anyone still have a question? Because we are already, 1 hour and a half, so maybe like 2 more minutes, Hans, if that's okay, and then
Yeah, that's fine.
Yeah, can I ask
Yeah.
also one more question?
Sure.
yeah, and Jake
Hans,
also liked, so Yeah, Jake, and then Ali. Sorry, Ali.
Yeah, my question is, if you could have multiple photons that were entangled, um, and send those through the fiber, is that possible? And would that increase your rate of entanglement?
Yeah, so it sounds like a solution, but it actually makes it worse. Because the problem is that, so okay, say you have kind of the easiest case. We have we will make then two photons entangled with one NV center. So that means that if we're in the zero state of the NV center, both photons are there, and if the NV is in the one state, both photons are not there, right? So this is, but the problem is if you lose one of these photons, um, losing it means that there was kind of a measurement process, right? Because somewhere in the fiber it got absorbed, and this absorption is a measurement. So it's kind of slamming down the coins on the table. And the problem is that if you lose one of these two photons, it also measures out the spin and your other photon. So, for example, if you absorb the other photon, that means it was there. That means that the other photon is now with 100% probability also there, and your spin is going to be in the zero state. So instead of transmitting this information, you measured your system, and it is not in a superposition anymore. It is not entangled anymore, and you can't make entanglement anymore. So, kind of, the whole trick is to send only one photon that's entangled with your spin. Everything that you do more makes the system more, or makes the probability of success only lower.
That makes sense. Just a quick follow-up. How do you generate a single photon?
So what we do is we put our NV center right in the qubit state, so in 0 or 1. So if we want to have a single photon, we put it in the 0 state, and we send out in a readout pulse. It excites it to the excited state, and if it falls back the NV center, it can only emit one single photon. So then there's only one photon. And that's how we generate these single photons, by putting the NV center in the zero state or in a superposition, shining in a laser, and then the NV center will emit only one photon or no photon.
Okay. I'll have to do more research on that one, but that
Yeah,
sounds
it's really fascinating. But this is yeah. So you can also use it indeed as a single photon source.
Thanks.
Ali, please go ahead. Thank you.
Sure, thanks, Katrina. So my question is about, let me say in this way, as you know, for example, the trapped atomic qubits normally, they are normally appreciated in the quantum circuits for their short interactions, high fidelity, and also relatively long, long quantum memory. However, we know the constructing of a stable quantum network, or in constructing the stable quantum network, the atomic assembly can be considered as the preferred candidate for the long range interactions. I'd like to know if your experiments can give us a better understanding of long range quantum teleportation, between light and macroscopic materials, or we still have lots ahead of us
Yeah,
to be in that
thank you for
step.
yeah, thank you for your question. I'm not sure whether I agree that it's clear that cold atoms will be the preferred system. So I think they have some amazing capabilities, but the challenging part of building a quantum network is that it's not about the highest purity of photons coming out. It's not about the gate fidelity. It's not about the entanglement rate, but it's about combining all of this together. So currently, it's quite challenging for cold atoms to store information, because you can't store information while reading out your system, right? We can read out our electron and still preserve our memory qubit. For cold atom experiments, you need 2 different species, but that's already more challenging. So I'm not sure whether the cold atoms will be the best in the end, and I think this is kind of currently the open question in our field, which type of system will fulfill all of the requirements together, right? So you want to have a bright system. So the NV center is not really bright. It's okay, but not really bright. You want to have really good spin properties or qubit properties. You want to have a very long memory qubits. You want to be able to integrate it probably on a chip or in some high volume. So I think this I see as kind of the challenging part, to combine all of the things together. And then I think there are still quite a few candidates out there, including the trapped ions, cold atoms, but also really the defects in solids, and not just diamond, but also silicon carbide or maybe silicon in the future, to fulfill all these requirements at the same time and be used as a quantum node.
Yeah, thanks, Hans. Yeah, well, the crystallographic defects in crystalline materials, plays a big role in everything we can say. Yeah, thanks a lot, and also thanks, Katrina, for the opportunity. Have a wonderful rest of the day.
Yeah, thank you so much. And yeah, thank you so much, Hans, for giving us all this time and sharing your work with us and answering all of our questions. This was really very interesting and amazing how you explained everything, and we really appreciate, and thank you everyone for asking great questions to make this to also help making this room like really interesting. So yeah, thank you, Hans, and
Thank you for inviting me. I really enjoyed it.
I hope, are you continuing your research in this field? Maybe you come back in the future with more updates if you would like. That would be amazing.
That would be great. Yeah.
Perfect. And yeah, enjoy the rest of your week. And yeah, again, we really appreciate everyone here, and especially you, Hans. And yeah, follow the club if you like rooms like this. We have a couple of days where we have actually 2 rooms. So tomorrow we have Dr. Pandey talking about a new epigenetic treatment for anxiety disorder and alcohol use disorder. And then we'll have Dr. Cassidy in the evening talking about locus coeruleus degeneration in Alzheimer's and novel techniques to develop to disentangle this insight. And on Wednesday, we have Dr. Vogt from Germany joining to talk about brain signal pathways that control food intake. And Dr. Campisi talking about CD8 T cells that characterize ALS disorder. And on Friday, we'll have Dr. Liang. He will join us to talk about deep sea virus that was discovered and gives us some more insights of the origins of complex life. So yeah, will be a continuous interesting week. So follow the club. And Hans, thank you again so much for this amazing talk. We really appreciate it.
Yeah, thank you so much for coming. This is a completely fascinating talk. Incredible.
Yeah,
Thank you.
thank you.
Nice to hear.
Yeah, thank you so much for coming. And thanks everyone for asking such great and wonderful questions.
Hey, thank
Okay.
you. Bye.
Bye. We'll close the room in 3,
Bye.
2, 1. Bye.
Bye, everyone.